In this video, we are going to introduce our newest work about an underwater leveling motion scheme, utilizing Singularity for a morphable unmanned aerial aquatic vehicle. Many rotor-based UAAVs today rely on large attitude changes for underwater movement. This is key because big attitude changes can mess up sensors, like cameras, affecting localization and risk losing track of targets and complicating tasks. In the previous work, our proposed vehicle can avoid these problems, but is hard to control underwater without any controller. Unlike other approaches that aim to avoid Singularity, this article proposes a scheme that leverages Singularity. Before introducing the scheme, a key concept is presented in this video: the singular thrust tilt angle, abbreviated as STTA. For the first time, STTA is defined and derived from the motion model of UAAVs. It is identified as the specific thrust tilt angle that leads to the vehicle's singularity, as shown in the block diagrams of different channels. From the analysis of STTAs for generating underwater leveling motions, 4 key discussions are raised. Consequently, a scheme named Aqua Slide is proposed to generate underwater leveling motion. It is designed under a switching-based framework consisting of an STTA controller and an auxiliary controller, incorporating a saturated Nussbaum function. Then, to validate Aqua Slide, we constructed a setup for simulation and experiment. As you can see from the screen, we implemented Aqua Slide on a Pixhawk mini flight controller and used it for both self-developed hardware-in-the-loop simulation and experiments. As you can see, in this comparison test, the pitch channel becomes uncontrollable after turning off the Nussbaum function. But once it's reactivated, the channel stabilizes again, proving the necessity of this function in the control framework. As you can see now, operating on the STTA of pitch, the vehicle achieves longitudinal slip motion. Combined with the heave subsystem, it enables depth-fixed motion, and with the heading subsystem, it allows for turning motion. Another comparison test demonstrates the auxiliary controller's role in composite motions. As seen in the video, when the auxiliary controller is turned off, the vehicle starts to generate a roll angle, but once turned back on, the roll angle stabilizes. As we currently observe, in the physical experiments, the vehicle successively generates underwater leveling motions like lateral slip motion and longitudinal slip motion. The attitude angle response graph in the bottom left corner shows that throughout the process, the Aqua Slide keeps the attitude angles stable within a small range. The underwater view in the bottom right corner clearly visualizes the entire process. Unlike in the hardware-in-the-loop simulations in this comparative experiment, turning off the Nussbaum function led to catastrophic outcomes for the vehicle. Ultimately, as seen in the video, a set of comparative experiments without the auxiliary controller was conducted. While not resulting in catastrophic outcomes like the previous experiment, comparing it with experiments that included the auxiliary controller reveals that during turning, the coupling and mutual influence between different channels led to the generation of additional attitude angles. These series of simulations and experiments are sufficient to prove the effectiveness of the Aqua Slide.